Every time you use a generative AI, stream a movie, or see a complex scientific simulation, you're witnessing the power of high-performance computing, or HPC. The demand for AI and machine learning applications is causing an explosion in the need for powerful HPC systems in data centers. But all that computing power is useless if the servers can't talk to each other fast enough. This requires incredibly high speed and low latency connections. So here's the big question. Is the traditional networking technology that powers our everyday internet, the TCP/IP stack, good enough for the extreme demands of AI and HPC? The answer is no. And in this video, we're going to explore the solution, a technology called RDMA, and specifically, a protocol that's taking modern data centers by storm, RoCEv2. To understand why we need something new, let's look at how computers traditionally send data over a network. When an application needs to send information, it doesn't just hand it to the network card. First, it has to make a copy of the data and hand it over to the operating system. The OS, using the TCP/IP stack, processes the data, adds headers, breaks it into packets, and makes another copy. This involves the CPU at every step. Finally, it sends it to the Network Interface Card, or NIC, to be sent out. This process is reliable, but for HPC workloads, it's a disaster. All of those copies and CPU interruptions add up to one thing: latency. And as network speeds get faster, the CPU has to work even harder just to manage the network traffic, creating a bottleneck. This is completely unsuitable for HPC. Now, look at this. This is the RDMA approach. RDMA stands for Remote Direct Memory Access. The name says it all. It allows an application on one server to read or write data directly in the memory of another server. The magic here is that the entire operation is offloaded to a special network card, an RNIC, and it completely bypasses the operating system and the CPU. It's like your application is accessing local memory, but that memory is in a completely different machine across the data center. The result? Sky-high throughput and incredibly low latency without burdening the CPU. RDMA isn't just one single thing. It's a concept that can be implemented using a few different network protocols. Let's quickly go over the main ones. First, you have InfiniBand. This is the gold standard, the native RDMA technology. It's a channel-based system that offers the best performance with high throughput, low latency, and built-in congestion management. The catch? It requires its own dedicated switches and network cards, which can be expensive. Then there's iWARP, which stands for Internet Wide Area RDMA Protocol. Its big advantage is that it runs RDMA over the familiar TCP. This means you can use your standard Ethernet switches, and you get TCP's reliability for free. But it still needs special iWARP-capable NICs to offload the work from the CPU. And finally, we have RoCE, or RDMA over Converged Ethernet. There are two versions. RoCEv1 works at the Ethernet link layer, layer 2, which means it's super fast but can't be routed. All your servers have to be in the same broadcast domain. This brings us to the star of our show, RoCEv2. RoCEv2 solves the limitations of version 1 by encapsulating the RDMA traffic inside UDP and IP packets. This simple change is a game changer. It means you can now route RDMA traffic across different networks, both L2 and L3, combining the performance benefits of InfiniBand with the flexibility and widespread use of Ethernet. So why is RoCEv2 becoming so popular in hyperscale data centers? Because it lets them run super fast RDMA traffic on the same Ethernet infrastructure they already use for everything else. No need for a separate expensive InfiniBand fabric. But there's a crucial catch. For RDMA to work properly, the network must be lossless. RDMA protocols are built with the assumption that packets won't be dropped. If a packet gets dropped, The recovery process is slow and kills performance. Traditional Ethernet, however, is lossy. It's designed to drop packets during congestion. So, to make RoCEv2 work, we have to teach our Ethernet network not to drop packets. This requires careful configuration. Let's look at the key ingredients. MTU, Maximum Transmission Unit. RoCEv. Two packets have extra headers, so you need to configure your network with larger frame sizes, typically jumbo frames with an MTU of at least 9,000 bytes to avoid fragmentation. QoS, Quality of Service. You must prioritize RoCEv2 traffic over regular traffic. This is done using something called DSCP marking, which tells the switches to always handle the RDMA packets first to ensure low latency. PFC Priority Flow Control. This is the most important tool for creating a lossless network. Imagine a network switch's buffer is getting full. Instead of dropping incoming packets, PFC allows the receiving switch, switch 2, to send a special pause frame back to the sending switch, switch 1. This frame tells switch 1 to stop sending traffic for a specific priority class for a fraction of a second, giving the buffer time to clear. Once the buffer level drops below a safe threshold, X on, traffic resumes. PFC essentially prevents packet loss due to congestion. However, PFC has a dark side. It can cause a problem called head-of-line blocking, where pausing one congested flow can end up blocking other, unrelated flows that just happen to be behind it. This can hurt overall network performance. DCQCN, Data Center Quantized Congestion Notification. To avoid relying too heavily on PFC's stop-start mechanism, RoCEv2 needs a smarter, end-to-end congestion control system. This is where DCQCN comes in. DCQCN uses ECN, or Explicit Congestion Notification. Here's how it works. When a switch, the congestion point, detects its buffer is starting to fill up, it doesn't send a pause frame. Instead, it just marks a special bit in the IP header of the data packets passing through it. It's a gentle warning that says, "Hey, things are getting busy here." The packet, now marked, arrives at the receiver, or the notification point. The receiver sees the mark and generates a special Congestion Notification Packet, CNP, which it sends directly back to the original sender. The sender, now the reaction point, receives this CNP and does the smart thing. It slightly slows down its sending rate. This is a much more elegant solution. Instead of the network coming to a screeching halt with PFC, DCCQCN allows the senders themselves to proactively manage their speed, preventing congestion before it gets bad enough to trigger a pause. The best practice is to use both PFC and DCQCN together. DCQCN acts as the first line of defense. It's the fine-grained, proactive mechanism that manages most congestion by telling endpoints to slow down. PFC then acts as the fail-safe. It's the safety net that kicks in to prevent packet loss during sudden, massive traffic bursts that DCQCN can't handle alone. This combination gives you a robust, high-performance, and lossless network perfectly suited for the intense demands of RDMA traffic. In conclusion, as AI and HPC continue to shape our world, the underlying network infrastructure has to evolve. Protocols like RoCEv2 are making it possible to build these incredibly high-performance networks without starting from scratch. By combining the direct memory access power of RDMA with the flexibility of standard Ethernet, data centers can achieve massive performance gains, streamline their network management, and reduce costs. However, as we've seen, it's not just plug and play. Unleashing the full power of RoCEv2 requires a deep understanding of the underlying network and careful configuration of features like PFC and DCQCN to create that essential lossless environment. When done right, it's the invisible engine powering the next generation of computing. Thanks for watching. If you found this helpful, Hit the like button and subscribe for more deep dives into data center tech. See you in the next one.